The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
You have to make some design decisions, and then once you've made those design decisions, then you can actually write your level 2, level 3 requirements and so forth. So it's an iterative process. So when you look at the classic V model, you don't really see those iterations, but they actually exist. So what we typically do at this system requirements review is review and then agree on the high-level requirements, level 0, level 1, maybe level 2 requirements, but not the lower level ones, because you can't, because you typically haven't done the design yet, right? The other thing I want to say is this is really a critical issue, and a lot of the problems we talked about last time, schedule, cost overruns, really a lot of these things are traceable back to the requirements. Either the requirements were over-ambitious, you set requirements that were essentially unachievable, or you missed requirements that actually became clear later on, but they weren't written, so nobody paid attention to them. A couple examples. So I have sort of one example of poor requirements, and then a good example. So this is a mission that you may have heard about. 1998, MCO. So who was born in, I'm looking at you guys, Justin, right? Justice. When were you born? 94. Okay, so you're older than MCO by 4 years. So MCO was a very well-known, just about 20, not quite 20 years ago, a very well-known mission failure that happened. Mars Climate Orbiter. It was launched on December 1998, and it had multiple functions. Study the Martian climate, weather, and surface changes, and it was to act as a relay satellite for the Mars Polar Lander, which came after it, and also failed. Both failed. And unfortunately, MCO burned up. We think contact was lost with the spacecraft after it basically entered the Martian atmosphere, and nothing. There was no more communication, so we don't know for sure. But the best guess is that the spacecraft burned up in the approach to Mars, that the actual altitude at which it entered the Martian atmosphere was about 57 kilometers, and it was supposed to be about 220. So even though the Martian atmosphere is very thin, when you enter at very high velocities, that's not a good thing. This is the very famous, you've heard about this confusion of units problem, right? This mission that one part of the team used SI units, specifically Newton seconds. This is momentum, right? Force times times time, that gives you momentum. So when you burn your engines for X number of seconds, that's the product of those two is your momentum. And then another part of the team used English units. Pounds of force times seconds. Okay, and so that was fundamentally the problem that caused the burnup. Now, if you read the accident report, and I have a link here to the accident report, you will notice that the requirements were actually okay. The requirements were written correctly. So specifically, there was a document called the Software Interface Specification, SIS, that specified everything should be in SI units on the ground segment and on the space segment. But the problem is that this was not checked and implemented. And so here's a quote from the accident report. Items that the mission assurance manager, which didn't exist for this mission, so the mission assurance manager's role is to make sure the requirements are actually followed. There was no mission assurance manager on the MCO mission. Included ensuring that the AMD file, which is one of the files put out by the propulsion system, met the requirements of the software interface specification, and that did not happen. Okay, so that was that was sort of the root cause there. Here's a good example for requirements. This is a little bit older. This is the DC-3. This is an old airplane. First flight in December 1935. Okay, this was really an airplane that kick-started civil aviation as a commercial service. And so, first of all, the DC-3 was based on an earlier evolution of the DC-2. And I first saw this when I worked in St. Louis. There was a little museum at the headquarters, and they had like a nice plaque on the wall with actually a replica of the contract. You know, the original letter that led to the DC-3 contract. And the story is that these requirements, this is level 0 requirements, what's written here, was hammered out in a single quote-unquote marathon phone call between Smith and Douglas. So Smith was at the time the head of, you know, what's today essentially United Airlines. And Douglas, who by the way is a graduate of this department here at MIT, Donald Douglas was the head of the Douglas Aircraft Company. And here are the requirements. Range about 1,000 miles. So this means that you don't have transcontinental range, right? If you want transcontinental range in the US, you need about how many miles? Like Boston to San Diego, Seattle to Miami, 3,000? Yeah, with reserves, yeah, 3,000 miles. So this means that if you go transcontinental with the DC-3, you got to refuel twice, basically. But you know that was okay. Today we probably wouldn't accept that, but that's okay back then. Cruise speed about 150 miles, 20 to 30 passengers depending on the configuration, twin engines, and then something that we would say today that's not a well-written requirement because it's fuzzy, but it said it should be rugged and economical. Right? And based on this sort of high-level requirements that were pretty clearly defined, the airplane was then designed, built, and very, very successful. And over 10,000 copies of this airplane were built. Okay? So what happened since then is a requirements explosion. This is a chart from a document called the Technical Multidisciplinary Design Optimization White Paper. And it's a little dated, but the basic message here is pretty stunning if you think about it. So first, heavier than air flight, 1903, the Wright brothers, right? 1G flight. What is the requirement for 1G flight? Get off the ground, and stay off the ground for, you know, at least a few seconds, right? Not just ballistic. That's the requirement. Get off the ground. Heavier than air flight. Yeah, big success, big milestone. Well, pretty clear after, you know, not too long, it was, well, we also want to turn. We don't want to just fly straight on the beach and land again. So maneuvering, gust accelerations, there's wind buffeting. You got to handle those gusts, so that's important. And then what were the first airplanes made of? Let's see at EPFL. Guys, what the first airplanes, what materials did they use? Wood, yeah. What else? Canvas, yeah. Exactly. So then very soon after that, maybe in the 20s and 30s, we started using metals, right? Metallic structures. And the big issue there, especially if you're flying, you know, close to the ocean and salt water, is corrosion control. Your airplanes can't rust. And so corrosion control became important. And pressurization. What is that all about? Higher, faster. So at some point, you need to pressurize the cabin, right? That's a new requirement. The Wright brothers never thought about that. Well, they didn't. Maybe they thought about it, but they certainly didn't have to pressurize their Wright flyer. So you see what's happening is we get greedy. You know, we're excited, we can fly now, but now we want to go higher, we want to stay longer. So we get greedy and we go to more extreme environments and so forth. And as we do that, it gets harder to do, and more requirements start piling up. And you see a big step here, World War II, right? Handling qualities, radar transparency. Radar was invented. So now you want to have airplanes that are not as visible on the radar. Fatigue, rough field landing. And then we have another big step here in the 60s and 70s. This was during the Cold War. Smart weapons, nuclear, fly-by-wire, right? Replacing cables with electronic flight controls. And then a lot of the illities in the last 20 years. Producibility, affordability, supportability, etc. So if you actually look at the requirements set for the new generation of airplanes, whether commercial or military, it's overwhelming. I mean, it's thousands and thousands of requirements because we've gotten greedy, and we've gotten good at it. So we keep adding more requirements. And that's a big issue right now. We'll talk later in the semester about complexity management. But the key message here is requirements have been growing over time. More and more requirements added as systems grow in performance and complexity. So here's some standards. I won't go through those in detail, but people recognize in the system engineering community how important it is, these requirements. So in the system engineering handbook, there's 2 sections, 4.2, which is about technical requirements definition, and then section 6.2, which is about requirements management. So definition means that's the initial definition of the initial requirements, and then management is the process of updating them, adding requirements, modifying them, making sure they're up to date. There's a couple appendices. In COSI, the International Council of System Engineering has in the handbook a whole section. There's even a requirements working group, people who really specialize in this. And then as well in the ISO standard, you have a lot written about requirements. So this is really a big deal. So the last thing I want to do here in this section is to sort of at a very high level communicate to you what requirements really are about. What they are about is, like I said, don't set off in your ship you don't know what port you're sailing to, right? So requirements set goals and constrain the design and the objective space. So whatever you're designing, you're always going to have 2 spaces that you're dealing with. The design space, on the one hand, that's the things you can choose as a designer, right? These are the knobs you can turn, the decisions you can make. And then the objective space, which is the things that essentially your customer cares about. And I'll give you a quick example here. So when we use the word shall, which I'll get to in a minute, the English word shall means this is essentially a constraint. You must accomplish this. And if you use the word should, it's more like a goal. It would be nice to do this, but it's not absolutely mandatory. So shall is a hard constraint. Should is a desirable and is a goal. So let me give you this quick example here. So let's say you're designing a house. You're about setting out to design a house. And what would be some requirements for a house? So I wrote 4 of them here. And I'll map them to the design space and the objective space. First requirement, the house shall sleep between 4 and 6 people. Well, is that in the design space or in the objective space? That's in the objective space, right? Yeah, that's right. So here we have an axis called occupants, right? So 4 is the minimum and 6 is sort of the maximum. So that's the upper bound. The next one, the total build cost should be less than $550,000. Should be. What is that? Maybe at EPFL.
A goal.
It's a goal. Yeah, that's right. And is it in the design space or the objective space?
Objective space.
That's correct. So I put this as a dashed line, okay, because it's a should. So what I've done here, just by writing these 2 sentences, these 2 requirements, is I've essentially carved out a space, right? And I can shade that box. Basically, what these 2 requirements do is they put a box around in the objective space saying that whatever house you're going to design, it has to fit within this box. Okay. Then the third one is the house shall have at least 3 bedrooms. What is that in the design space or objective space? Design space, right? Because defining a bedroom is a design decision, right? And then the house should have a fireplace. So you can show the lower bound here, at least 3 bedrooms, and then the fireplace is it would be nice to have, but you don't absolutely have to have it. So you can sort of draw this. It's more like a line here, right? Yes, fireplace, but it's a dashed line, and then at least 3 bedrooms, right? So just these 4 sentences, we've now put we've defined the space that we're going to be designing in. So we have constraints in the design space, and we have constraints in the objective space. And that's fundamentally the role of requirements, is to constrain, to give us direction as to what we're going to design. Okay, so let's do our first concept question for today. And that's the following question. Do you think there's a fundamental difference in the meaning between the words requirements, which we've talked about so far, and then the word specifications, which I haven't mentioned yet? So no, you think they're essentially the same. Yes, there is a difference. Requirements are like the input, and specifications are the output of the design process. Yes, you think a difference. Specifications include the requirements as a subset, or you're not sure. So think about this, and then submit your answers. And as far as these URLs are concerned for the concept questions, I went to all lowercase. Hopefully that's a little easier. So SECC3, tiny.cc, SECC3. What do you think? Requirements and specifications. Same thing or not? Who needs more time? Anybody? Okay. Uh-huh. Okay, so we have nobody thinks they're the same. 2/3 of you think that requirements are the input, specifications are the output. 9 of you think that that requirements are a subset, and then 6% are not sure. So that's good. I agree with that. So a lot of people use requirements and specifications as the same thing. They're really not. Okay, so think of requirements as you haven't actually started the design yet. This is you're putting constraints in the design space, defining the direction, but you don't actually know what the design will look like. You may have some requirements may say you must use this box, or you must use this sensor, right? And you might actually find some of those in the CAN set. But basically the requirements are the input. So what are your experiences? When have you heard those terms, requirements or specifications, used interchangeably or not interchangeably? Has this come up as an issue for you before? Marissa, you've worked on human space flight, right? Space tourism vehicles. So how did you guys do it at Virgin Galactic?
Well, I think something that you generally saw was like people would look at sensors, and there's a specification for a sensor, and they would not necessarily compare the requirements to the specification. Or they'd not understand like how the two intersected. So I think there was a bit of a misunderstanding of the difference between what the actual requirements were versus what the specifications were designed to be.
The sensors you're talking about would be sensors, I'm assuming, that you would purchase, right,
Mm-hmm.
as commercial?
Yeah, absolutely. So I think we're buying off the shelf, and so I mean, sometimes the specifications were broader than what we wanted, sometimes they were narrower, but you can do additional testing, and so there was sometimes a breakdown between understanding really whether the sensor met what we were looking for or it didn't.
Okay, good. What about at EPFL? Any experiences? Volker, you worked on slip rings, right? Slip rings was one of the big specialties of your company. I'm assuming that you guys had to make that distinction, right, between requirements and specifications. What are your thoughts at EPFL on this?
Well, yes, on our side, we clearly had the separation also on an ESA level. But I was wondering here in the class, has anybody ever seen the difference between specification and requirements? Any comments? Maybe some of the PhD students that have been around the block. Christoph?
Well, most of the time when we ask our managers to come up with a design, we work with requirements as an input. We give specific targets for functions of subsystem of automation. And well, we haven't spoken yet so much about specifications, but for me the meaning comes somehow naturally with what your system would be able to achieve.
Yeah. Okay. Great. So I found here I wanted to sort of find an example that everybody can relate to very easily. So the answer is there is a distinction. They are quite different, but you've got to be careful because people mix them up. So requirements specify what the product or system shall or should do, right? Functions it shall perform, how well it should perform these. Also maybe the degree of autonomy, how automated is the system, so what the operators must do when the system is operating. Also compatibility with other devices. And then specifications are about how the system is built and how it actually works. So the form, right? What the materials that are used, the dimensions, schematics, blueprints, the details of the user interface. Those are things. Those are all specifications. So I try to look up, a very simple consumer product that we all are familiar with. Microwave oven. Kenmore Elite countertop, 2.2 cubic foot. You go to Sears website, and what's interesting is they actually do a pretty good job. It's actually pretty consistent with what I'm saying here, except they don't talk about requirements. They call it description, right? So what's listed under description, and I'm pretty much quoting this here verbatim. This microwave is large enough to accommodate big dishes, right? So the idea, this is sort of family style, right? This is not a small microwave just for frozen meals. You should be able to put a big casserole in it and reheat meals and so forth. So the idea that what are the things you're going to use in the microwave? What's the use case, right? CONOPS for the microwave. Family, 4 kids, both parents are working. Busy, not time to spend 2 hours preparing dinner. Therefore, big dishes, a lot of people. It has to be quick, right? That's a CONOPS. And the requirements. This description is essentially the requirement. 1,200 watts of power to reheat food quickly. So time is important. And then one-touch settings for different food types: rice, pizza, frozen meals. And what is that? That's automation, right? Rather than having to guess how long and at what power level to reheat, there's some partial automation built in. That's essentially requirements. Very user-centric. Did you see that? And then when you look under specification, it says the following things: stainless steel exterior, right? Again, you don't want it to rust. The dimensions, the weight. There's a general warranty for 1 year. The power cord is included. You see, it's a very different. Those are things that describe how it's made, the form of it, and so forth. So make sure you keep those separate. Okay, so let me talk about the NASA requirements process, and then we'll talk about challenges. So getting back to the system engineering engine, that's sort of the heart of the NASA system engineering process. You remember this is the this happens at every level of decomposition. After stakeholder expectations, the second step is technical requirements definition. And there's some pretty strong language in the handbook that this really has to be done well. So the center directors or their designees shall establish and maintain a process to include activities, requirements, guidelines, documentation for the definition of technical requirements. So I think I've already said this, but I just want to make it clear again. This is a kind of, I like this cartoon. This is Moses, right? Up on the, Moses just got the tablets, right? The stone tablets. The 10 Commandments. And one of them is, thou shalt not steal. And God says out of the clouds, no, they're requirements, not goals, right? So what God is saying is the 10 Commandments are shall, right? And not should. Even though I think some of us don't always succeed at that, but that's basically the idea. Shall is a very hard constraint, and that's what you will be judged against. And should is essentially a desirable a goal, but the degree of attainment is somewhat flexible. Why are we doing this? Why are we spending our time writing technical requirements? It's essentially to transform those stakeholder expectations we talked about last time, transform them into measurable technical requirements. Requirements come in different flavors, and I'll mention those flavors, and we express them in these shall statements. They also provide a basis for agreement among the stakeholders and developers. So you will often find requirements part of contracts, right? That now it becomes serious. You know, when the requirement set actually has legal implications, you are legally signing up to develop a system that will meet these requirements. That's pretty serious stuff. By writing good technical requirements, you can reduce the development effort because of less rework. So a lot of rework and iterations and confusion is based on missing or poorly written requirements, right? And writing those early and before the design begins is helpful. A requirement set is also a basis for cost and schedule estimates. And so some of these missions that overran, do you remember I showed you this chart last time? We analyzed 40 missions, Earth and space science missions. Like 20% of them were responsible for 80% of the overruns. A lot of that had to do with unrealistic goals or expectations and requirements. And then the next point here is the requirements provide the basis for verification. In other words, the better, the more crisp, the better written your requirements are, the easier it is to test the system and to check whether the system is in compliance with the requirements. And then eventually the basis for acceptance. Acceptance is also a big deal, right? It basically means I accept your design, I take ownership of it, and I say you as a developer of the system have done your job properly. And there's a legal transfer of the asset that happens. So facilitates the transfer of the product to the users. And then even later, if you're going to do like a version 2 or a block upgrade, a next generation product, it's much easier to do when you have the clear requirements because it tells you what the original system or the earlier version was able to do or not do. Graphically, so this is figure 4.0.1. I briefly talked about this last time. We start essentially here at the development. We have mission authority. We do the stakeholder expectations. Talked about that last time. And then here, right away, comes high-level requirements. So that means your level 0, level 1 requirements. And then as you try to get more detailed in the requirements, what do you think happens? Let's say ideally you'd want to write all the requirements up front, right? That would be great. But you try to do that, you hit a wall. Why is that? What's the issue? Why can't we just write all the requirements and then be done with it in one shot? Yes, go ahead.
Oh, your system changes over time, and some of the requirements clash, and you can't achieve all of them simultaneously.
Yes, so there's two things you mentioned. So one is the sort of, and I'll talk, this is known as requirements volatility, right? The requirements are changing as you learn more about the problem. And then the other is you detect conflicts between requirements, and you have to clean those up. Those are two very valid issues, but it's not quite what I was going for. Yeah?
There's another one, requirements creep, in which your customer levies new requirements on you once you've started the process.
Yes, so new requirements get added. Hopefully you get more budget too. That doesn't always happen, right? So that's another issue. But it's a little different. Let's see at EPFL, you guys, why don't we write like all 4 or 5 levels of requirements all at once? Why can't we do that typically? What do you think?
Usually some of the requirements aren't clear or they don't exist yet. Later on in the process they become clearer and you start to realize the details, which at first you don't.
Yeah, I think that's pretty close to what I'm looking for. So the issue is you do your level 0, level 1 requirements, and then sort of as you get to level 2, you can't really write a level 2 requirement until you've made some key design decisions. You know, are we going to use electric propulsion or are we going to use chemical propulsion? You know, that's a huge decision in space system design, and unless you've made that decision, you can't really write lower level requirements because the fundamental working principles of chemical and electrical propulsion are quite different. So that's the key issue, is that you can only do the high level requirements in a solution neutral space. And then you hit the wall because you've got to make some key concept technology selection decisions. And that's shown here by this red box called functional and logical decomposition. I don't like that nomenclature a lot. This should really say system architecture or concept selection, which we'll get into in the next couple of weeks. Once you've chosen a high-level architecture and concept, then you say, okay, we're going to go for ion propulsion. Well, then you can write the requirements for the ion propulsion system, which are defined in this yellow box here. So this is your design and product structure, derived and allocated requirements at lower levels. You see that? That's the fundamental. All the things you said, requirements creep, requirements conflicts, all those things are true. But the fundamental reason why we can't write all the requirements up front is because at some point the lower level requirements depend on design decisions you make. Okay, that's the fundamental issue. Okay. Any questions about that point? Yes.
It's not totally about that point, but it's still like, so requirements versus specifications. So if you're like, buying a component from a vendor, some piece of hardware, and you want to identify like the specific locations where it should attach to things, it's more of like a form as opposed to really, so does that fall into requirements or is that like a specification?
Great point. So what you're describing is a particular type of requirements that we call interface requirements. And it's a perfect segue to this next, if I could only include 5 slides in this lecture, this would be one of them, okay? This basically is what are the different flavors of requirements or types of requirements, and there's 6 of them here. So first of all, the functional requirements. I think we've sort of talked about those, right? Define the functions that need to be done to accomplish the mission objectives. There's some examples here around thrust vector control. So basically the idea here is that you have a thrusting system and it has, you can actually direct the thrust. And in this case, you should control the thrust. You shall provide thrust control around pitch and yaw axes. Okay? So this statement is a high-level functional statement, and it's written in the actor-verb-object form, right? So that's sort of the classic, the classic requirement is a functional requirement. And then we have performance requirements. The performance requirements are, in a sense, qualifiers on the functional requirements. So a performance requirement will specify how well the function should be performed. How fast should it fly? How much thrust? This is where you have to actually put numbers in. So in this case, this thrust vector controller shall gimbal the engine 9 degrees, right, That's the deflection angle, at least 9 degrees, plus or minus 1 degree, 0.1 degree. That's a performance requirement. Then we have constraints. Okay, yep.
Isn't the performance requirement saying the engine has to gimbal 9 degrees? Isn't that kind of pushing towards the specification? Or is that, I mean, I guess it can also be a requirement, but isn't that?
Right. In this case, we haven't said, we're not specifying how those 9 degrees are achieved. You know, whether it's through a gimbal or the actual mechanism or how is not described here. All that's described is the angular range, essentially. That is a performance requirement. But you'll see there'll be some examples of things that are putting limits on the form, which looks more like a specification. So then we have constraints. Constraints are things on like weight, mass, power, things like that. So constraints are requirements that cannot be traded off with respect to cost, schedule, or performance. So for example, the thrust vector controller unit module shall weigh less than 120 pounds. So that's not, if you think about it, that is not functional, right? The weight of this thrust vector controller shall not be more than 100. That is not performance. It's not functional requirement, but it's a constraint on the form, essentially, right? So this looks more like what we would call a specification constraint. The fourth one is what Marissa brought up. This is an interface requirement. Okay, so in this case, our thrust vector controller shall interface with the J2X. The J2 is a very famous engine, and J2X is a kind of this was written during the Constellation days of the Constellation program at NASA, is the idea of a new generation of the J2 engine. So the idea is that whatever you do, however you design your thrust vector controller, it must be able to interface with the J2X engine according to conditions specified in this interface control document. So this is called an interface requirement. Then the fifth category are environmental requirements. So the TVC shall use vibroacoustic shocks and loads according, again, to some environmental document. And by the way, for the CANSAT competition, we have that, right? There's two documents. There's a mission guide, and then there's this environmental testing guide. So what this essentially says is, under what conditions shall the performance and the functions and performance that are specified in the first two type of requirements, under what conditions shall that be performed, right? And if you think about it, designing, whether it's a sensor or anything to operate between, 0 degrees Celsius and 30 degrees Celsius, or between minus 60 and plus 80, is a huge difference, right? You can write that down, but what that actually means to open up the range of environmental conditions, it has big impact on the design, right? So this is a big deal in practice, and at least in space systems design, a lot of these environmental requirements are of course driven by the space environment or the launch environment. If you're designing airplanes, whether you're flying in a small mountainous country like Switzerland or on the ocean off of an aircraft carrier, those are very different environments, and they're going to influence. You have to specify the operating requirement. The bigger the envelope that you make for the environmental requirements, the more complex the system will be. Also, anybody working on medical devices here? EPFL, anybody? Medical devices? So in medical devices, it's the same thing. Is this medical device going to be used in a hospital setting, where everything is kind of clean, you have clean power, the nurses, everybody is very well trained? That's one thing. Or is this medical device going to be used in the field, in Africa, in India, in a rural area where people are maybe not trained medically, professionally, and so forth? Very different. The function may be the same, but the environmental conditions are very different. So you have to really specify those. And then we have, the last category is kind of other. it's sort of a catch-all, but this can be very important. So this includes a lot of the human factors, reliability, and safety requirements. Those are, and you know, they're listed here as other, and I think it's really important to say that just because they're listed here doesn't mean they're less important. These are often neglected, unfortunately, and it really can hurt you in the long term. So pay attention to those human factors, reliability, and safety requirements. So 6 types of requirements. So let's talk about what makes good or acceptable requirements. And there's a distinction here between a single requirement statement and then sets of requirements. So first of all, requirements should be written in natural language. They should be complete sentences. And each of the requirement statements should be clear and consistent, meaning that it's not a novel or it's not a poem, but it's clear, it's understandable, it's well written, it's correct, there's no errors in it, it's feasible. Now that's a really tricky one. That's the first thing here that's really tricky when you think about it. Feasible means what? It means this requirement can be satisfied within the laws of physics and state-of-the-art technologies and other project constraints. So why is that a tricky one? Go ahead.
Well, I was going to mainly ask a question regarding that in terms of how do you deal with a program where you're working on things where you're trying to actually maybe define the state-of-the-art or figure out what is feasible.
Right. So if you're basically designing a product or a project or system that's a repeat of what's already been done, then you can have pretty good confidence, right, that those are feasible. But what if you're doing, let's say I think I mentioned this last time, you're going to Europa and you're going to drill through the ice and you're going to explore the ocean under the ice sheet in Europa. It's never been done before. Can we actually do this? So this is the tricky thing. How ambitious can the requirements be, and you still can claim feasibility? And that's also one of the big reasons why programs get in trouble, is when they're actually defining requirements that are not really feasible within, they're definitely way beyond the state of the art, and within the time frame and budget allocated, you can't get there. And many programs that run into this problem are the ones where the technologies that you're going to use are not really ready yet. We'll talk later about technology readiness level scale. You're not really ready yet to do this, but you're going to try anyway. So that's the tricky one, feasibility. Flexibility is don't over specify how things should be done, so don't state how it should be satisfied. Without ambiguity, that means, if 10 people read this requirement, they should have the same or very similar interpretation. A singular statement, one actor, verb, object, and then the last point here is verifiability. How are you going to check whether or not this requirement is in fact satisfied?
With regard to the feasibility again, for some of these programs that have large overruns, schedule overruns, would it be almost better in a sense to have some of the requirements be almost shalls, goals? In other words, if you can do this, go for it, but if you're going to run over 10 years, maybe back off a couple percent.
That's right, and we'll talk about this a little bit. But if all of them are shell statement, they're all hard constraints. The objective space, that I showed you, may in fact have zero feasible space, right? So really knowing what is a hard constraint, what is a hard requirement, and what's flexible, that's very tricky, and that's why it's important to actually not just accept requirements. If you're going to run a project, every requirement you want to really understand it, and if you think this requirement is infeasible, you have to negotiate. That's where the upfront negotiation becomes really important. Did we lose our EPFL? Okay.
No.
Go ahead, please.
Oliver, I would have a comment here, maybe.
Please, go for it.
So in 1990, we got the requirements from NASA to build a space bioreactor, and all you students will love this. It was the smallest brewery that ever flew in space. And the initial requirement was that all fluid containers had to be solid with double walls. And this meant that we had another solution with bladders, soft bladders, so we had a real fight up front in the proposal phase to demonstrate the compliancy to the requirement of doing the cell culture, the yeast cell culture, and still being non-compliant actually to this requirement of hard double-walled fluid containers. And so this is exactly the point. Finally, these flew, and they've still been flying now since the last 15 to 20 years. And this was a breakthrough in technology, and there you will always have these challenges with the agencies, with your customers, because they are used set in their ways, and you have to demonstrate the feasibility, and then to make then a change in requirements that allows you to change the specification.
No, I think that's a great example. So in the end, you were successful to argue for the bladder solution?
Well, the bladder was just how to keep the fresh medium and the used medium, meaning the beer. The technology we wanted to put in there was MEMS technology for space, and actually it needed to have flexibility on the pressure in the reservoir. That's why the argument to put MEMS in space finally won the day and allowed to relax the other requirements.
Yeah, thank you. The great example there. Any other comments? Okay, so all this is a pretty long list, and this applies to single requirements. And then there's a set of, this is really important, then there's a set of characteristics that we want to see when you look at sets of requirements, groups of requirements. Absence of redundancy. This means that each requirement is specified only once, right? You don't want to have redundancy. Redundancy can be good in system design, but not in the requirements, okay? Consistency, using terms. Completeness, and this basically means not missing key requirements. And then this idea of absence of conflicts. And this is also similar to the feasibility. This is a tricky one. Requirements can be in tension with each other, particularly if they're should, right, goals. But they shouldn't be in direct conflict with each other. Like, you know, you shall use aluminum for this unit, and then another requirement says no metals are allowed to be used in this unit. That conflict is not solvable. That's a direct contradiction. That's different from having competing requirements or requirements in tension. So let's do a quick exercise, and then we'll actually take a break as well. So this is a turn to your partner exercise, and then we'll have a break, and we'll restart in like about 7 minutes. So here's what I'd like you to do. I have 3 systems here. They're very different in scale and complexity. So A is a sticky tape, and I'll tell you the quick story here. I grew up in Switzerland, surrounded by farms, you know, and I spent all my times at the farms, and, you know, big tables, big families. And they have these things here. This is basically, these are flies sticking on tape. This is keep the flies off the dinner table. It's called Mr. Sticky tape for trapping flies. Really kind of gross, but I remember it. B is, I just a couple of weeks ago had a test drive in the new i3. This is the BMW small electric city car. Very cool. And then C is something that at EPFL you guys know very well. This is the Rolex Center. It looks kind of like Swiss cheese when you look from the top. This is the sort of equivalent of our W20 here at MIT. This is the student center. So there's library there, there's cafeteria there, and so forth. So what I'd like you to do is turn to your partner, pick one of those 3, and come up with one single statement, one good requirement that you think was possibly used in the development of that solution, whichever one you pick. Okay, so pick one of those 3, and then jointly discuss and write a requirement that you think led to this design. Okay, so take about 5 minutes, take a break, and then we'll sample what you came up with. So let's hear from EPFL first. Who did anybody do A?
Who did A?
Okay, go for it.
A.
Speak up.
We have 4 requirements.
Okay, go for it.
All right. So the tape shows 6 flies. The cost of the tape should be less than 4 francs. The tape shall be able to catch up to 50 insects, and the sticky tape shall not be toxic for humans.
Okay, I like, the toxicity. That's good. Excellent. Very good. Who did A here at MIT? Anybody? A? Go for it.
We said if greater than 10% of the surface area of the fly contacts the paper, it shall not be able to release itself.
I see. So this is a trapping requirement.
Yeah. How effective should it?
There are very different flies, right? There's like these little day flies, and then there's the huge horse flies. So which type of fly does this apply to? Oh,
we said 10% of the surface area of the fly.
Of any type of fly?
Of any type of fly.
Any of the different fly species?
Yeah.
Okay. All right. Cool. So good. Well, the point of this, you get the point of this is, right, A is like, this sort of, you think trivial system, but once you really start thinking about it, it's pretty tricky, right? Who else wants to, A, something that hasn't been mentioned yet on A? Sam, go for it. Just push, make sure you push the button.
Yeah, for the sticky trap, we said that the product shall fit on a store shelf when packaged.
Okay, so that's kind of a packaging, logistics, distribution requirement. Very good. Mike?
They kind of already touched on it, but the sticky tape shall not be toxic and allow removal of human skin without bodily harm.
Okay, great. So that's in the same, human factors requirement, basically. Yeah, very good. Anything else on A at EPFL? No.
Well, it just comes to mind here that we could say that the sticky system should be installed without getting the mess on your hands.
Okay, so installation requirement. Okay. Nobody mentioned, the ones I remember as a child are bigger than this. They were really long. So capacity, right? You could sort of have a length or capacity requirement as well. Good. All right, I think we want to move on from the sticky flies to BMW i3. So we had a little discussion here during the break. Lucy, go for it.
So the car shall meet environmental regulations through mechanical or software tweaking was a proposal.
Did you guys hear this at EPFL? You've been following the news, right, with Volkswagen? So what happened? Why did the CEO just step down, right? That's kind of a big deal. Trust in the company has eroded. What happened there?
So the requirements that were set at the start, so the car shall meet environmental regulations on emissions. This requirement was probably not met, but the realization that it wasn't met was probably too late in the design process, such that it cannot be changed. And so the easy or cheap way to meet environmental regulations in that case was to tweak the software, I guess.
Right. So, by the way, this is kind of interesting. How do you measure environmental compliance of emissions for cars? Do you know how that's done in practice? Do you guys know?
So it's having the gun run on having the engine run, but the car's not like rolling, and there's behind the exhaust. Yeah. Behind the exhaust, you measure whatever is emitted.
And it's like on a rolling carpet, right? It's a dynamo basically, and the way they do it is they have so-called drive cycles. Like there's the FP6 drive cycle, the highway, the city cycle, which is a lot of on and off, And those drive cycles are actually different in Europe and the US and other countries. Every country has different drive cycles. So and what is a drive cycle essentially? What word would we, as systems engineers, what word would we put?
Con-ops.
A drive cycle is just over time, accelerations, velocity of the car, right?
It's a con-ops.
It's a con-ops. A drive cycle is a con-ops. And so for diesel engines, this issue that happened with Volkswagen, it's only an issue with the diesel, the TDI engines, right, not the gasoline engines. So the issue is that the con-ops, the drive cycle in the US with TDI engines, they couldn't meet it. So they came up with this trick, right? Whereas in Europe, they didn't have to do that. Because the European drive cycle, there's a lot more diesel engines used in European cars. They didn't have to do that in Europe because the con-ops, the drive cycle that's used for checking the environmental compliance, is different in Europe. So great. Anybody else on the i3? Now the i3 is interesting because that's actually an electric car, right? And so it doesn't have an engine, a diesel engine or a combustion engine, except if you get the range extender. So it's all electric, but you can actually, it's an option, get the range extender, which does use fuel. Okay, EPFL, the i3, any other requirements there?
So we have 4 to begin with, like the car shall rely on electricity as unique source of power. Then a second one is the autonomy, so the car should drive at least 150 kilometers in city driving conditions, like the cycle we just talked about.
Yeah.
As a third one, the car shall carry 4 to 5 passengers of average build. And to finish with, the car should be fully recharged in less than a given amount of time.
Okay, so recharging. The third requirement is interesting. You said of average build, right? That's the word you used.
Yes.
Now, that's great. That's a human factors requirement. Now, of average build is a little fuzzy, right? How would you make that more verifiable?
The thing is that if we just say 4 to 5 people, it's very broad. You could have someone who is very large and someone who is very small. So the idea here is to stress that you have to use a model. Maybe you could be more specific and say 75 kg, 180 and so on. But we wanted to see the choice.
Yeah. So there's actually people that the size distribution, male, female, weight, all these anthropometric measurements are actually being recorded and updated. People are getting taller around the world. People are getting heavier. We know that, right? So the way you would write that third requirement to be verifiable is the car shall accommodate 4 passengers between a say P10 female or P5 female and a P90 male, right? And if you write it that way, then the actual weight and dimensions of the human body can actually be traced to a database that's pretty well known. So then instead of saying average build, you say it's a P50 male, P50 female, and that's something that's very verifiable. Does that make sense?
Yes.
Okay, great. So what about the last one? So by the way, here at MIT, anybody's been to EPFL? Been to the Joanna doesn't count. She has a master's from there. You don't count. Anybody else been there? This is a very cool building. It's pretty unusual. I mean, we have some very unusual buildings on campus too here, but if you get a chance, it's pretty unusual. So let's hear from you guys. So what do you think was a requirement for the Rolex Center design?
The building should be a recognizable structure that would be memorable for EPFL.
Ah, interesting. A recognizable structure that should be memorable. So I think I know where you're going with this, but it's a little, recognizable. Every building is recognizable in a sense, right? I think I like it. I know where you're going with this, but it's a little fuzzy still, right? So why do you think it has holes in it? Why do you think the holes?
To let in light. I think unique. Unique might be a better word. And it's Swiss cheese. So
Swiss cheese. So yeah. So that's really the holes are in some sense inefficient, right? Because you're putting holes in the middle of a building, but they provide natural lighting, and there's a symbolism there, right? There's a symbolism, the Swiss cheese symbolism. So the holes in a sense have at least two functions, right? That's good. That's good. I like that. That's very good. What else? Another example of a requirement for the Rolex Center?
We've taken an example in each category. In functional, we said that Rolex Center should house a library, a cafeteria, and facilities. In performance, the Rolex Center should meet the energy citizens' expectations. In constraints, the Rolex Center shall be accessible even for disabled people. Interface, the Rolex Center shall interface with the existing internet network. And environmental was a little bit fuzzy because we did not have any clear requirements.
Good. No, that was great. So you had functional requirement, you had interface requirements, you had a lot of those 6 categories we talked about, right? Very good. Excellent. Yeah, go ahead.
So how do you write a requirement about something aesthetic in a way that's not fuzzy? Or is there a way to do that?
That's a great question. I'm not sure I'm the best person to answer that. What I can tell you is in the automotive world, that the aesthetics of automobiles and how people judge, whether a car is beautiful or appealing, that's actually moved from being kind of just a very fuzzy thing to quite measurable. The different shapes and the building blocks of shapes and streamlines, those things are, that's really a science today. And eventually, there's ratings. These are, people rate vehicles for aesthetics and so forth. And usually it's a 5-point scale, like a Likert scale. Like J.D. Power and Associates is a very well-known marketing firm. And so they'll say they can actually at this point you can show them not a sketch but a model, and based on past data and information, they'll tell you this car will probably score between a 4.2 and a 4.4 on the 5-point aesthetic scale, J.D. Power scale. It's really pretty remarkable. But I guess the bigger point is there's some some things that really delight us, that have an artistic quality, surprise us, an aesthetic quality, and it's true that is one of the tensions. Is yet system engineering should this very precise, write it down, make sure there's no fuzziness there or as little as possible, and then on the other hand, we want delightful, surprising things, right? That have an artistic nature to them, and that is absolutely a tension, and we just acknowledge that. Okay. Any questions, comments before we move on?
I had a question about.
Just hang on, just one second. Okay, go ahead. At EPFL.
To which extent can we refer to norms and laws in the requirements?
Yeah, you should do that. So compliance, being compliant with standards, and just to make clear, standards and regulations are not the same, right? A standard, like an IEEE standard or an ISO standard, it's not a law. It's not a legal thing. A standard is something that maybe a group of companies or a group of organizations have agreed to. This is how we will do it, right? The IEEE Wi-Fi standard. What is it? 802.11g, right? That's not a law. That's a standard. And if you're going to be 802.11g compliant, you write that in the requirements. The environmental emission standards we talked about, those are actually laws. If you are going to sell a vehicle in country X, it has to comply legally with these regulations. But you're absolutely right. Those are, if you need to comply with these things, it needs to be part of the requirements set, because otherwise it will not happen just automatically. Okay? Weston.
Yeah, it's kind of along that vein. If you have to comply, say, with ADA, does that have to be called out specifically, or do you say must comply with building codes or building laws, and it's sort of a blanket requirement?
No, you have to be specific, because building codes are, first of all, a lot of these are local as well, and it's very chaotic. And some of these might be conflicting, so you should be as specific as possible. Okay, let's move on here. My sense is you're getting a gist for what requirements are and why they're important. So let me talk briefly about requirements decomposition, allocation, and validation. This is a figure from the NASA handbook, and basically what it talks about is, the high-level system functional requirements are broken down into the performance requirements, and then as you make design decisions, as you decompose your system into different subsystems, each subsystem will have its own functional and performance requirements. And then the important thing is the difference between allocated and derived requirements. So allocated requirements are requirements that you choose to allocate, and then derived requirements are calculated based on they're dependent requirements based on the allocated requirements. And I'll get into this in a minute. So requirements are hierarchical. We talked about this. Functional and performance requirements are allocated, and then from these we can further decompose and derive requirements. And then the total set of these requirements needs to be verified and then validated against the stakeholder expectations. So let me briefly talk about requirements margins management. So because you don't know everything up front, there's uncertainty, we typically build in reserves into our requirements, and those are called margins. So we put in margins for mass, power, maybe memory in computer systems. So margins are essentially reserves that are not allocated to particular subsystems, but are controlled by the project managers or at the higher level. So the idea is that you write the requirement in a way that is a little bit more stringent than it really needs to be. And then by being more stringent, you build some reserve into the system to handle unexpected things. So I'll just give you the example with mass growth. This is very typical in aerospace vehicles. Mass growth can range between, here 10 to 60%. I'll show you some examples. And a lot of it depends on the novelty of the project. So a typical guideline, specifically for mass margins, is about 30% reserve at the SRR, 20% PDR, 10% CDR, and keep about 5% right before you operate the system. IOC is initial operating capability. So here's some historical data. This is for manned or crewed vehicles. Starting with Mercury, Gemini, Apollo, Skylab, and then the shuttle, you can see the mass growth from the concept stage, which is phase A or pre-phase A, all the way to operations, between 10 and 60%. The new Orion spacecraft is not yet included on this chart. So what you do is you essentially write the requirement knowing that this growth will happen during the design process. That's the basic idea of margins. And then the next idea is that you monitor the satisfaction of the requirement during the design process. And so let's say you have, in a performance requirement, you say that the system shall not emit more than X number of NOx, right, emissions, or the system shall not be heavier than such and such. That's on the y-axis here. That's your technical performance measure. And then you move through time, and as the design gets more detailed, usually it gets heavier, you add more things, and you monitor that. And then you have your final current estimate of where you will be at the end of the project. And as you do that, your limits, your reserves, your margins, and here there's an upper and lower margin shown, is going to be narrowing down. I'll give you a quick example. When I was at McDonnell Douglas, the F-18EF version, the Super Hornet, was being developed. And the key thing there was GTOW. GTOW, gross takeoff weight. It's basically the weight of the airplane with crew, fuel, any payloads, all in. The gross takeoff weight of the airplane is very important because it determines the range, it determines a lot of things. And the number, not to exceed number, which is shown here on this chart as the maximum contract or allocated requirements threshold, was contractually specified. Not only that, but there were penalties, financial penalties associated with every kilogram that you would be over. So this was a big deal, and they had a huge wall chart in the hallway, the main hallway of the engineering building, and every day somebody would actually manually update that day's best estimate of what the gross takeoff weight of the airplane would be. And it's like a Brownian motion thing, and as soon as you hit some critical threshold, you would see people would come together and say, we got to take weight out of the airplane somehow, again, right? And then basically try to get the design to comply with that requirement as you move through the design process. You can't do that with too many of the requirements, but the most important technical performance measures, that's what you do. It's a big deal. So here's the flow chart basically for requirements. I'm not going to go through this in detail, but the basic idea is the inputs come from the stakeholder expectations, the stakeholder work we talked about last time. You go through the requirements definition process, and out comes a validated set of technical requirements, measures of performance that you can measure, and then these technical performance measures that you can then track and validate against later. Here's a question that I often get asked. Well, okay, so we write these requirements, you guys write them on paper or your tablet, but how do these requirements actually get recorded, right, and managed? So I would say there's sort of two, there's the low cost, and then there's sort of the professional version of doing this. The easy way to do it is you just write them, you capture them in a document. So that means, Microsoft Word, Excel, Google Docs, just a document, a well-written, organized document. And then you capture and revise your requirements. And the one thing I strongly recommend is using hyperlinks to link requirements. And this is the idea that every requirement has to be linked to some other requirement. So if it's a low-level requirement, you want to ask, well, where does that come from? Why did we write that requirement? Well, it has a parent requirement. So you want to have a hyperlink there to get you from one to the other. And I have a little example for that. And I think this is okay for smaller projects where you have dozens or a few hundred requirements, right? And so here's my rule of thumb for this. Do you remember the magic number 7? So we talked last time, where does the world of really complex systems start? And the argument was, well, if you need more than 3 levels of decomposition, what does that mean? Well, 7 plus or minus 2 to the 3rd power is somewhere between 125 and 729, right? So if you're sort of in that world, or fewer, right? If you're in a few dozen or a few hundred requirements, kind of what we have in CANSAT, it's okay to do it this way, right? It's still going to be, a lot of requirements, and you have to do a good job, but you can do it that way. If you have more than that, and that typically means more than 1,000 requirements to handle, and there are big projects that have 5,000, 10,000 requirements, there is no way you can manage that effectively in a kind of document-based way. So what you need then is a database. You basically capture these requirements in a relational database that allows you to link each requirement to other requirements. And so this is not meant as an advertisement, but one of the most heavily used requirements tools out there is called DOORS. And this was relatively recently bought by IBM. This was a separate company. It was bought by IBM and included in a suite of software tools called IBM Rational for system development. And so DOORS allows you, it's a database, relational database, it allows you to write requirements, share requirements, and the latest version of DOORS is actually web-based, So you can have people, in India, in Europe, in the US, you're co-developing a system. You can all write requirements and manage them on this common database, right? Because if you have a document, very quickly it's going to be confusing as what's the latest version, who has, the latest update. Version management becomes a nightmare. So just so you're aware of this, we're not going to be using doors in this class. We'll just do it document-based, but the rule of thumb here is more than 1,000 requirements. You've got to go to some professional solution. So here's a very sort of trivial example of hierarchical requirements with links. Requirement 1, the system shall fit into a volume not exceeding 1 cubic meter. And then we have sub-requirements. The system's width shall be between 0.5 and 1 meter. The height, the depth. The system shall be made entirely from aluminum 6060 alloy. A sub-requirement here is the system shall not contain any internal voids or cavities. Requirement 3, the shape of the system must be a cube. And then a sub-requirement, the angles between the sides shall be 90 degrees plus or minus 1 degree. And so, and I did this here just in the slides, but if you click on this, it'll actually transport you to another requirement. This is requirement 4. The mass of the system shall not exceed 2,700 kilograms, right? Aluminum has a density of about 2,700 kilograms per cubic meter. So if I click back, it transports me back to the earlier requirement, right? So the fact that it's made of aluminum and the volume cannot exceed 1 cubic meter, then this requirement 4, the mass shall not exceed, it's not independent requirement, it's a dependent or derived requirement based on the first two, and therefore they're linked. Do you see how this works? And to really manage requirements well and then link them, use these hyperlinks. It's very, very effective. So what would be an object that satisfies these requirements? So here's our 1 cubic meter envelope. So an aluminum cube with a side length of 60 centimeters, this volume and this mass, would satisfy the requirements. It's not the only thing. There's a lot of other geometries that would satisfy it, but this particular instantiation would satisfy these requirements. Okay, so that's the idea of hierarchical requirements, linking them through hyperlinks. Okay, so let me talk briefly about the challenges now of requirements definition. And this is not easy. There's a lot of challenges. The first one is requirements allocation. There's decomposition and flowing requirements to lower levels. And the idea is that whatever requirements you derive at a lower level, if you satisfy the lower level requirements, that should guarantee that you then automatically satisfy the higher level requirement, right, from which the lower level requirements were derived. That's the basic idea of requirements allocation. And so the way you can think of this graphically is we start at the high level. Here's our stakeholders, right? Stakeholder needs, requirements. This is level 0. You set the system boundary. What's the life cycle? And then we apply it. That's our first application. And then we apply it by decomposing the system into its functions. And so that's the second application. And then you say, well, how will these functions be carried out? So we define subsystems. And essentially then the subsystem requirements are derived from the functional requirements. And you put numbers, key system performance parameters behind these. And depending on the complexity of the system, you may have to go multiple layers down. But that's the basic requirements allocation process. And I think I said this already, it's difficult to do and stay solution neutral the deeper you go into this. Let me briefly mention, this will not be, we will not sort of test you on this, but I want to make you aware of this. A methodology called isoperformance, and that was actually the topic of my dissertation. How do you allocate requirements to lower level parameters or systems when the higher level requirement is defined, is clear? So the idea is that you have a vector of desired performance requirements, and you want to understand, first of all, are those requirements feasible? And if they are feasible, it usually means there's more than one way that these requirements could be satisfied, that the higher level requirements could be satisfied. So find different non-unique feasible combinations to satisfy the higher level requirement. And so this is one of the readings. Very quickly, we have our design space, we have our objective space, and then we have this cost-risk objective space. And so the idea is that in the performance space, you have the shall statements. You shall perform at that level. And that's this point here. That's your performance target. And if it's in this gray area, it's actually feasible. And it usually means there's more than one way to do it. So if you can then map backwards to the design space, these points here are all isoperformance, meaning they all satisfy and provide this level of performance, but they do it in different ways. And then in order to select a final design or a final requirement set, you want to look at other objectives. This is where the should statements come in, and these are typically cost and risk related objectives. So let me give you, this sounds pretty abstract and theoretical. Let me give you a very specific example. This was my main case study, a space telescope. This is the, actually, this has now become the James Webb Space Telescope. Hasn't launched yet. This is 20 years ago, right? We've been working on the James Webb for a long time, but if it works, it'll be exciting because it's going to get us very, very close to the Big Bang, right? That's what James Webb will look in the highly redshifted infrared to really see the formation of the earliest proto-galaxies in the universe. So if this works, it'll be very exciting. So here's essentially a model of the spacecraft. This is a precursor to the James Webb. And the big thing you need to do is you need to point and be very, very stable for a long time to take in these very, very faint images. So we have wavefront error phasing requirements, and then we have these pointing requirements. You've got to point very stably. And in order to achieve this optical pointing performance, we have the structure of the spacecraft, we have reaction wheels, we have controllers, and there's noise, different kinds of noise sources that are trying to basically prevent us from pointing with this precision. So very quickly, this is what this Nexus precursor spacecraft looks like in the deployed configuration here on the upper right, in the stowed configuration. Initial performance assessment. So this is really trying to find the requirements for deriving the requirements for the structure, for the optics, for the controller, knowing that this is the point. If you want to have this science happen, you've got to point with that precision. That is known. So let's flow that down. So if we look at the pointing, for example, here on the right, this kind of fuzzy fur ball, what does that represent? That's a time domain simulation of the centroid of the image, right? The telescope is now observing a part of the sky, trying to get these early proto-galaxies, and it's flexible. It's a very lightweight telescope. It has these reaction wheels are turning, trying to keep it stable. We have electronic sources of noise. So the blue fur ball here predicts that we would not meet the requirements. This is some initial design, some initial set of requirements. We need to find a way to get down to the, this is about 15 microns root mean square error, so it's about 3 times worse than what we need to achieve. And the requirement is we need to get down to 5 microns of pointing or jitter precision. So how do we do this? So what isoperformance does is it looks at the sensitivities in the system. What are all the things that influence the pointing performance of the telescope? And you can see here, these are the 2 key performance measures. On the left, wavefront error, and then line of sight. And the bars essentially tell you what are the really sensitive parameters that drive performance. So disturbance parameters, plant, structural parameters, optics, and then controls. So it's really multidisciplinary. And what's neat about it is you can, if you know these sensitivities, you can essentially calculate the Jacobian matrix. The Jacobian matrix is essentially the partial derivatives of your performance, right, which is your higher level requirement, with respect to these lower level parameters or requirements. And you can then find, using this, essentially the null space of the Jacobian matrix that will tell you how do you move in that space to keep the performance fixed at the requirement level. let me explain this just using 2 parameters, okay? And this was a big deal on the Hubble Space Telescope. So the 2 parameters I'm going to use is KR ISO and UD, the dynamic wheel imbalance. So these spacecraft have reaction wheels that are turning to point the spacecraft and counteract any momentum that you get from, for example, from solar pressure. So UD is the amount of imbalance that you have in these wheels, right? If you have imbalance, that will cause chatter, it will cause torques, which will cause that jitter. And then KR ISO is it's a vibration isolation of the reaction wheel assembly. How stiff or soft is the vibration isolation? And what you can see in this plot is that our initial design, this is based on a simulation, does not satisfy the higher level requirement. In order to satisfy that, we need to go down to this blue line labeled with 5 here, right? 5 microns of pointing precision. And what you can see is that there are different ways to achieve that 5 microns. We could go over here. This is labeled as HST. That's what Hubble Space Telescope did. The Hubble Space Telescope basically went for ultra, ultra, ultra quiet reaction wheels. Very, very low dynamic imbalance. So, Marissa, you talked about, buying sensors from a supplier and putting it in. There's companies that really specialize in making reaction wheels and things like that. So if you're going to go for this point here, let me point that out again so you guys can see it at EPFL. If you're going to derive and allocate this requirement, it means you put a lot of pressure on your supplier to achieve that level of dynamic wheel imbalance. If they can do it, that's great, but it could be very expensive. But it makes your job easier, right, as the spacecraft integrator. Or you could go straight down this point here called spec. So you're essentially tolerating a noisier reaction wheel, but then you need a very, very soft, very capable isolation stage, very soft isolator. What's the disadvantage of having very soft isolation? What do you think is the big issue there? So the launch, you probably have to lock it down during launch. You have big displacements. You need if you have a very soft isolation stage, you need volume because the isolator is going to move a lot, right? And you may not have that volume. Or you could do a little bit of each. So this test point here means we're going to have quieter wheels, but not ultra quiet, and we're going to have a soft isolator, but we have the right combination of the two. And we're going to go for that point there. So now if you go for that point, you're going to satisfy your pointing requirement, but you've allocated the lower level requirement, in this case, to the isolation stage and the dynamic wheel imbalance in a kind of balanced way. So everybody's job is roughly equally difficult. That's the sort of idea here. Yes?
Does this model assume that all of these variables are then independent and I guess kind of continuous in terms of, you can incrementally work better?
So they're not independent in the sense that they're coupled through the performance of the system. But you can choose, the assumption is you can choose these independently. But they're coupled because you need to achieve that requirement. And yes, in this case, they're continuous, but you can think of this as discrete as well. So, for example, the reaction wheels could be you picking from a catalog, for example, right? In which case, now you're really picking specifications for components that are off the shelf, right? Okay, so I'm going to skip here for time. So basically, following this ISO performance process, you can go from some initial requirements, derived requirements that are infeasible, to, and in blue here, I'm showing you the results of this. It's very close to 5. There's some numerical tolerance here, but by essentially rebalancing the requirements within the system, we're achieving the higher level requirement, but in a way that distributes sort of the challenge equitably across subsystems. Does that make sense? At EPFL, did you guys follow this? I know this was a bit fast, but that's the basic idea of ISO performance. Any questions on your side?
No, thanks.
Yes, maybe I have one. So given that you have different requirements and you probably have ISO performance lines for each one, is there a way that would kind of integrate all those lines that you could see the feasible region for those, you don't mind, maybe it's a little bit softer, but maybe there's another requirement where that's a really sticky point. Can't hear you.
Yo, we don't hear you.
Sorry, guys, we ran out of battery here. Can you hear me again? Can you hear me? Yeah? So the question was, well, if you have multiple of these ISO performance lines, that's exactly right. If you have a vector of high level requirements, you're going to have ISO performance surfaces. And so it gets, the more of these you have to satisfy at the same time, the more complex this gets. But we can handle that computationally. So you have to do some simulation and computation up front to make sure you pick. These requirements are not just wild guesses. They're actually based on some calculation and simulation. Okay? All right. So here, let's do this. Let's do this in a kind of simplified way. This is going to be our last concept question for today. Here's the higher level requirement is a balloon. Those of you that have done unified engineering here, you've done this, right? We did this in unified. A balloon shall lift a payload of 1,000 kilograms, which includes its own mass. You can use either helium, which has a density of 0.2 kilograms per cubic meters. This is in standard atmospheric conditions. Or hydrogen, 0.1. I've rounded these numbers. As a lift gas, the standard density of air is 1.3. Which of the following requirements is infeasible? A, the balloon shall have a radius of 6.1 meters, and the balloon shall use 99.9% pure helium. B, a radius of 5.9, and the balloon shall use 99% hydrogen as a lift gas. And then 5.9 meters helium, 6.1 meters hydrogen. E, all these requirements actually are okay, or none of these requirements are feasible. Okay, so I'll give you 3 minutes to try and figure this out, and then I'll show you the solution. Don't cheat. Don't go to the next chart. So think about this. The high-level requirement is the balloon shall lift 1,000 kilograms, including its own mass. And we're trying to allocate lower-level requirements for the size of the balloon and the gas that we're going to use. So try to figure this out. All right, I think we probably who needs more time for this? Okay, so we're going to leave this as a cliffhanger, okay? We'll do the solution next time, and take a little time to figure this out. Try not to look at the next slide, okay? So I'm going to skip this just for time, and I want to talk briefly about the SRR, what it is, and then kick off assignment 2. So SRR, so the idea is you've really been working on these requirements hard, as a team with your customers, and this is not a quick thing. This is not just 2 or 3 days. Typically, writing your level 0, level 1 requirements is a process that takes weeks, months, sometimes at least a year. But typically it's on the order of 3 to 6 months in many projects, roughly. And once you have your high-level requirements, SRR is the milestone where you review those, right? So here's an example. So it's a peer review process. And the main goal of SRR is to vet the requirements as they were written, to see if you have any missing, misstated, redundant, or otherwise unsatisfactory requirements. This is a picture from JPL, from MSL, actually, mission. And I want to just point out a good friend of mine who's a graduate here of our department, Richard Kornfeld. Volker knows him, met him last summer. He's been working on 3 different Mars missions over the last decade. And we're going to hear from Richard later this semester about verification of requirements, because he verified the entry, descent, and landing requirements for MSL. So here's essentially what it says in the NASA handbook. SRR happens during phase A, before you go into phase B, and you need at least your top 2 level requirements written before you can do the SRR. I do want to mention the second reading, post-reading. This is about requirements volatility. So just because you pass the SRR doesn't mean that the requirements are completely frozen. First of all, you don't have a lot of the lower level requirements yet, right? Those are going to be added post-SRR. And even some of the, you pointed out, some of you, the requirements creep and these things. So this second reading is about requirements volatility, which you can actually quantify. What are the sources of requirements volatility? That's what this figure shows you. And then what is the impact of requirements volatility? What is the impact of requirements volatility on a project? So specifically, on the number of system requirements, on rework, on project schedule, and so forth. It's a very, very recent paper on requirements volatility. So let me just kick off assignment 2, and then we'll be done. So assignment 2 goes out today and is due in 2 weeks, so that's October 9th. And it's very focused on requirements. Basically, what I want you to, and it's the same teams that you're in for all the assignments, is essentially, first of all, first task is find a project or program where poorly written or managed requirements were a major problem. So as a team, discuss an example and discuss that example as a team. The second task is look at those CANSAT 2016 requirements, those 47 base requirements, and analyze those critically. So that means, are they feasible? Are they well written? Classify them, what type of requirement is it? Is it an interface requirement? Is it a performance requirement? And then figure out whether there's a hierarchy there. And basically then, from that, generate your own set of requirements for the CANSAT competition. So you're going to either rewrite or reorganize these requirements in a way that's better and that works for you as a team. And then the fourth requirement is to figure out where you want your margins. Where do you think you need to have reserves and margins in these requirements? Okay, so it's very much looking and reorganizing and critically analyzing the CANSAT 2016 requirements set. So let me summarize. Good requirements are really essential. It's the starting point for system design, system engineering. It is a challenging thing, especially the flow down is challenging. There are some methods and commercial tools for doing formal requirements management. So I mentioned ISO performance, and then I mentioned DOORS, these commercial tools. And then the last point here is just because you passed SRR and you have high-level requirements approved doesn't mean that's the end of the story, right? The requirements will continue to be updated, refined, but you have to be very disciplined to keep that in check. If your requirements volatility is too high, then bad things can happen to your project. And I really recommend the reading on requirements volatility, some very, very recent data on that. Okay? So that's the end of the session for today. I'm going to be online on the WebEx in about 10 minutes. If any of you have questions or any comments or you want to dive into this further. I know this is not a great time for you at EPFL because it's Friday night for you guys. So I think what we're going to do, we'll figure this out with Lise and Joanna. We'll see if we want to do a separate time, a different time during the week for the office hours. I'm happy to do this at a better time if this doesn't work for you guys because it's happy hour time for you. So anyway, okay, so great. Have a great week, and we'll see you next Friday.